Hello everyone, my name is Brian Choi and I am from Johns Hopkins University. I'll be presenting Understanding and Dealing with Hard Faults in Persistent Memory Systems, a work done with my advisors Randall Burns and Ryan Huang. So first, a brief summary. We introduce a new class of faults in persistent memory systems called soft to hard faults. We have an in-depth study that examines the characteristics of 28 real-world PM hard faults and 7 large systems. Then we discuss our solution, Arthas, that uses dependency-based rollback in order to recover and mitigate PM hard faults with minimal data loss. So in today's modern society, whether it's a large distributed application or some personal computer software, errors inevitably occur in applications and computer systems. When this happens, it can be a frustrating experience. However, when a critical error in your system occurs, generally what's the first thing you do? Most people tend to just restart their computer or application, as it's the simplest solution that many times leads to the problem going away. The reason why restart works is because these failures are soft. Where soft means that your states are volatile and your bad states will be gone when you restart. But there unfortunately do exist hard fault problems where this restart approach doesn't work anymore and the bad states will reoccur even after restarting. This problem is particularly going to be problematic with emerging persistent memory systems, and I'm going to explain why. But first, a little background on what persistent memory is. Persistent memory is a newly emerging storage technology that has byte addressable latency comparable to DRAM while being able to persistently store data like a disk through power failure. Previously, developers tended to avoid persisting too much data since existing block-based storage options tend to be too slow to access reliably during runtime. However, with persistent memory, developers now have the option to persist a much larger amount of data more frequently, since PM is such a fast storage technology. For example, we could persist a previously volatile cache so that the system can restart with a warm cache. Since persistent memory persists many states, these soft states become hard states when they move into persistent memory. And naturally, any bugs or problems that occur with these states now become permanent. We call this class of bugs as soft to hard faults. If you look here on the left, you can see that we have a traditional system with some bad soft states, including some memory leaks, a corrupted hash table, and a corrupted cache. In a traditional system, you can see that after restart, these problems go away. For example, the garbage collector will end up cleaning up the memory leaks, the hash table will be reconstructed to not be corrupted after recovery, and finally, the cache will restart as a cold cache after restart. However, if a developer chooses to persist these states in persistent memory, then these problems will persist even after restart. For example, the persistent memory leaks will continue to exist after restart, and the hash table and cache will remain corrupted even after restart as well. Let's look at a real-world example of a soft to hard fault. Here, let's first look at a soft fault in traditional memcached. Here you can see how memcached is comprised of several items of key value data and also some client connection data. In standard memcache, the client connection data and items, including all the fields of the item, are all stored in volatile memory. However, with this specific bug, memcache ends up with two corrupted fields, the item's ref count and hash table next pointer, both end up becoming bad states. In standard memcache, we can see that since the items are in volatile memory, these two bad states end up going away after restart. However, several developers have made persistent memory versions of memcache, where the developers may choose to persist one or both of these bad states into persistent memory. As you can see here, several versions of persistent memcache choose to persist the entire item data structure in persistent memory while keeping the client connection data in volatile memory. As a result, since the items are now hard states, both the bad states end up remaining as bad states even after restart. So for our contributions, we did a hard fault study where we examined 28 real-world bugs in PM systems, and the memcache ref count bug that we went over just now is one example. We also created Arthas, a tool that aims to mitigate hard faults in PM systems while minimizing data loss using dependency-based rollback and static analysis in order to identify the program dependencies. So first, we'll look at our hard fault study. In our study, we found 28 bugs from 7 total PM systems that demonstrate the soft to hard fault problem. The first finding we observed from our hard fault study was that the root causes of PM hard faults are diverse. In this chart, you can see that there are different root causes of PM hard faults, and even though the vast majority of bugs are due to logic errors, there's still a healthy mix of a variety of root causes for PM hard faults. The other root causes are relatively evenly distributed at around 10 to 15% for each of them. Looking more in depth at the root causes of our bugs, first are logic errors, where bugs with temporary values end up having some form of problematic state due to a logic error in the software. For example, in Memcache's flush all bug, when a user states that they want the system to flush keys 86,000 seconds after the current time, what actually ends up happening is that Memcache can end up flushing keys before 86,000 seconds due to a logic error in one of their if conditions. Another root cause includes concurrency errors, which generally occurs when concurrent processes have some form of race condition leading to errors. An example of this is Memcache's hash table lock data race, leading to the state of Memcache's rehashing flag to be an incorrect value. We also talk about buffer overflow, which is a root cause where a bad input can cause the system to end up having a problematic state. An example of this is Memcache's int buffer overflow problem. When a user sends an append request packet to Memcache, if they state that the size of the body of the item should be 0 bytes, but the size of the key is 250 bytes, Memcache ends up writing to an allocated segment of memory that is 0 bytes, leading to a buffer overflow and a security vulnerability. We also have persistent memory leaks, where not freeing memory can lead to inaccessible memory. An example of this is PMKV's asynchronous lazy free issue. When PMKV has to free an item, it will unlink the item from its indexing structure and then assign a background thread to actually free the item later. However, if PMKV crashes before the background thread is able to free the item ends up becoming a persistent memory leak. Finally, we have hardware faults, where defects in hardware can corrupt program variables. An example of this is if there's a CPU bit flip in Redis, it can lead to an incorrect hash table size, leading to an assertion failure. The second finding we observed is that the consequences of PM hard faults are severe. In a chart here, we can see a large portion of the consequences leading to problems such as repeated crashing, wrong results, and data loss, all of which are significant, non-negligible problems for any system. For our third finding, we observed that over half of the PM hard faults propagates bad state. Here we can see a categorization of the PM faults, where type 1 refers to faults where a PM variable has a bad value that is a direct cause of the problem. Type 2 refers to faults where a PM variable propagates a bad value and doesn't directly cause a problem. And finally, type 3 refers to miscellaneous faults, such as memory leaks. We can see that 68% of the bugs are type 2 and indirectly propagate bad state throughout the entire system. As a result, we see that PM hard faults are a diverse set of bugs, and it can be difficult to statically find all bugs with one single static solution. However, from our study, we were able to see the insight that during runtime, eventually all the PM hard faults cause bad states to be persistent. So instead of statically analyzing error patterns and trying to create a different solution for every type of error, we instead try and approach the fault by reverting bad states to good states. The other insight we see is that since most of the faults propagate bad state, even when one bad PM state is rolled back, the PM system can still quickly hit the same failure if the root cause of the bad state isn't fixed. So we need a method to not only revert the immediate bad value, but also the root cause. We now ask the question, how do we revert the bad states? Our goal of effective mitigation is to find is complete when the hard fault is gone and doesn't reoccur after the system restarts. Therefore, for our solution, we aim to develop a tool that checkpoints previous, older versions of persistent states, so we can revert any bad states to previous versions, which are good states. And we need to roll back all the bad states, including the root cause. Naturally, one might ask, why don't we just use standard checkpoint and rollback tools? However, existing checkpoint and rollback solutions have their own limitations. In this example, we can see a PM key value store with 2 key value pairs when our checkpoint system takes a snapshot. Then, as we insert some key value pairs, we eventually crash when inserting the key 10,000 and first pair. Through some analysis, we were able to find that the root cause of the issue is caused by the 10,000 key value pair. So, standard checkpoint and rollback tools will roll back the entire system to the previous snapshot where we only have 2 key value pairs. As a result, we end up losing all the keys from key 3 to key 10,001, when there is only one bad root cause. This gets us to the main problem of standard checkpoint and rollback approaches. It causes a large amount of unnecessary data loss. As a result, for our tool, Arthas, we aim to avoid the problem of data loss that standard checkpointing has by using static analysis to find dependencies of bad states in order to only revert bad PM states instead of unnecessarily reverting any good states that may not need to be reverted. Looking at the properties of recovery that the two different recovery approaches have. First is the effectiveness of mitigation, and second is data loss. While it is true that standard checkpointing does end up fixing the system to a good state, satisfying the first property, but when you persist data in PM, it's implied that you do care about the persistence of your data, and losing data in applications that need to reliably store the data can cause severe damage. As a result, for these types of applications, we need to use a carefully designed solution to handle data loss properly. Our solution, Arthas, is a tool designed to mitigate PM hard faults in PM systems by checkpointing multiple versions of state, using static analysis and dynamic tracing to find bad state dependencies, and then use those dependencies in order to drive our reversion. As a result, Arthas will be able to recover PM systems quickly and minimize any data loss while incurring a small runtime overhead. Here we can see Arthas' primary workflow. First, our PM system code undergoes static analysis by Arthas' analyzer to construct our dependencies for minimal data loss during reversion. Then the PM system code is instrumented with checkpoint support, so that we can save multiple versions of our persistent states. Then the instrumented PM system can then run while creating the checkpoint log of multiple versions of data. The instrumented PM system will keep on running until the detector detects a problem, at which point the Arthas reactor will then mitigate the PM hard fault. First, we'll talk about the checkpoint library. As we previously stated, we need to checkpoint data in order to have multiple versions of our PM state, so we can revert any bad states to older good states whenever we run into a fault. We accomplish this by intercepting PM framework API calls and then assigning global sequence numbers to each PM update in order to ensure order when we begin reverting data later. Let's look at an example of this in action here. You can see that in our code, we allocate some persistent memory. So our checkpoint library will intercept the allocation call and then create a checkpoint entry by assigning the address of the PM pointer here. Then, when we assign a value of 7 to the PM pointer and then flush the bytes of the PM pointer, the value 7 is saved as the first version of the PM pointer's data, the global sequence number of 1 is assigned to this value, and we save the integer size of 4 bytes. Then let's say we change the value of the PM pointer to 4 and then flush it again. We assign the value of 4 to be the second version of our PM pointer data. We increment the global sequence number to 2, and then we keep the integer size of 4 bytes. The next component is the analyzer. As we talked about earlier in the talk, Arthas needs to only revert bad states and avoid unnecessary data loss. So Arthas' analyzer aims to use dependency-based rollback, where we use static analysis in order to get the data flow and control flow dependencies. In order to actually get these dependencies, we construct a program dependency graph of the PM system, where the instruction that causes the fault is used as the starting point of the dependency analysis, and individual slices of the PDG is used to see what instructions influence this fault. You can see an example of this in action here. This is some code with some persistent memory writes and volatile writes, where the blue segments are volatile writes, the red segments are persistent memory writes, and the arrows denote dependency. The system ends up crashing at the division instruction of variable z, since we divide by 0. However, we see that the root cause of the error was due to x, since this is the variable that initializes the value of -5 and causes the division by 0. In order to avoid unnecessary data loss, Arthas takes a slice of the PDG to only revert any bad persistent variables based on dependencies. So we can see that Arthas will create a slice of the dependent variables, where z depends on y, which depends on x. Then Arthas' purge mode will selectively revert only the PM variables on this slice, in order to fix the bad PM states while minimizing data loss. So we end up reverting the writes of x, y, and z only. As a result, we can see that Arthas' purge-based rollback allows us to minimize data loss. However, it doesn't necessarily guarantee a perfectly consistent system. As a result, Arthas also contains a rollback mode, a more conservative approach that reverts all variables between dependent updates. This rollback mode more carefully preserves dependencies of the system. For example, we can see that we also revert variable b as well, since it happens before the write to y, but happens after the write to x. While dependency-based rollback minimizes data loss, static analysis takes a long amount of time to construct the PDG. So, we move Arthas' reactor to use a server-client architecture, where as soon as the code is available, the server can begin constructing the PDG of the PM system offline. And the client will serve mitigation requests to the server whenever the PM system crashes or the detector detects a fault. Now, we'll talk about our evaluation. So we ran our evaluation on one 8-core CPU and two 128GB persistent memory DIMMs. We tested on 12 of our bugs from our study and also from existing bugs not from our study. We then ran Arthas against two baselines, PMCRIU, which is a state-of-the-art checkpoint and rollback system that does coarse-grained, time-based rollback where it rolls back to specific snapshots in time, and we modified CRIU to use persistent memory. The second baseline is AR checkpoint, an alternate version of Arthas that only reverts without the analyzer component and rolls back in a time granularity with fine-grained rollback. So we evaluated Arthas on 12 of our case study hard fault PM bugs. Each of these bugs are diverse with varying consequences, showcasing how Arthas is able to handle a large spectrum of bugs. We first evaluate Arthas' effectiveness, and Arthas is able to resolve all of the 12 bugs, while AR checkpoint suffers from timeouts and is only able to resolve 2 out of the 12 bugs, and PMCRIU is only able to reliably mitigate 9 out of the 12 bugs. However, effectiveness is only one aspect. Equally important is the data loss aspect, which we show here. Here we can see how much data the three systems discard, and our results show that Arthas discards up to 10 times less data than PMCRIU. See the recovery times that the three systems have, and Arthas is slightly slower than PMCRIU, but is still in an acceptable range, taking around 1 minute longer than PMCRIU while also keeping much more data. So this ends up being a trade-off between losing a large amount of data versus slightly slower recovery time. We then show the overhead Arthas' checkpointing and instrumentation adds. It only adds about 3 to 5% overhead compared to PMCRIU's 0.2 to 2.7% overhead. Some related works include crash consistency bug testing and detection, such as PM test, XF detector, and PM threads. However, these works focus more on PM ordering bugs, where unexpected crashes before ensuring all writes are written leads to persistent memory potentially becoming out of order or inconsistent after restart. However, Arthas focuses on a different class of bugs than crash consistency bugs. These bugs run during normal execution and can occur at any time even before the crash point, soft to hard faults. Another type of related works are checkpoint and rollback solutions such as flashback and ThigNVM. These revert the entire system using time-based snapshots that are taken periodically or some other coarse-grained time granularity. So they end up losing far more data than Arthas' fine-grained dependency-based reversion. So Arthas is unfortunately not perfect, as it still has some limitations that we reserve for future work. First, the static analysis that Arthas does for its dependency-based rollback doesn't scale well and can take a long amount of time for large systems such as Redis or Memcache, which have tens of thousands of lines of code. In addition, Arthas' purge dependency-based rollback means that you may end up with an inconsistent system. This is because Arthas relies on the program dependency graph for handling dependencies and total system consistency. But complex systems and scenarios, such as hidden dependencies, may lead to inconsistencies that Arthas' purge mode can't handle. Therefore, Arthas also has a rollback mode that prioritizes consistency over data loss. And although we have some other mechanisms, such as transactional consistency reversion, which we talk about more in a paper, we believe that future work can be done into this problem. Finally, Arthas is unable to handle distributed persistent memory applications that have external dependencies, and extending Arthas to support distributed PM applications would involve other solutions, such as vector clocks. In conclusion, soft-to-hard faults are an underexplored yet significant problem in new persistent memory systems, and Arthas reliably detects and mitigates hard faults in PM systems using dependency-based rollback in order to mitigate the faults and minimize data loss. Arthas ends up being able to mitigate 12 faults from 5 PM systems with 10 times less data loss than standard checkpointing techniques and a reasonable performance overhead. And our tool is publicly available on GitHub. Thank you.